our second lecture, we're going to canonically quantize the free scalar field. So just to recap what we did last time very briefly, so we gave some motivation and briefly reviewed classical field theory. The two key results to remember from last lecture are, one, Noether's theorem that you explored more in your homework, and the solution to the Klein-Gordon equation that we arrived at the end of yesterday's lecture. So that's going to play an important role moving forward. And just to remind you what that solution was, we left off last time, we found a mode expansion for the Klein-Gordon field. It solved the Klein-Gordon equation, the Euler-Lagrange equation for a free real scalar field, and took this form. Where, just remember here that K naught was EK, which was K squared plus M squared. So these are four vectors in the exponents, even though we're only integrating over three components. That's where we left off. That's what we're going to do today. So first, we'll choose a better normalization. Then we're going to canonically quantize this field. So just in a procedure very analogous to what you're used to from non-relativistic quantum mechanics, we'll promote instead of the position, the field, and its conjugate momentum to operators. And then we'll examine the states of in this theory. And already we'll find some surprising differences compared to what you're used to in non-relativistic quantum mechanics. In particular, many quantities that we naively would think we could compute will turn out to be infinite, and this will be a recurring theme in quantum field theory. And finally, so for the first part, this will take the bulk of the lecture. When we quantize the field and discuss the states, we'll be working in the Schrodinger picture. And if time permits, at the end of lecture, we'll discuss the Heisenberg picture. So that's where we're going today. Okay, so the reason that this form of the solution to the Klein-Gordon equation is not the most convenient one to work with is this measure. So this measure is not clearly not Lorentz invariant. It only involves a integral over the three spatial components of K. Over here, we've got nice Lorentz invariant arguments to the exponential. So that part we took care of last time. And if we make the measure Lorentz invariant, it'll make our lives easier later. It will mean that when we promote the field to an operator, these A's and A stars will get promoted to ladder operators. With this normalization, the ladder operators will create states that are not Lorentz covariant. So if we directly quantized using this mode expansion, there will be a bunch of extraneous factors that we'll have to keep track of. It'll just make our life more difficult. Whereas if we make the measure Lorentz invariant, it'll turn out that the ladder operators will create Lorentz covariant states. So the only thing we'll ever have to remember about Lorentz covariance is the measure. So it's a bit less to remember if we first make this measure Lorentz invariant. Okay, so the natural way to try to do that is to start with the manifestly Lorentz invariant measure, is an integral over 4 components. If we want to relate this integral over the 4 components of k to integral over the 3 components of k, then well, the natural thing to do is insert a delta, direct delta, to constrain, in particular, the 0th component equal to the energy. So we do that, insert a delta, and if we use this delta to do the k0 integration, well, we'll almost get what we want. It will constrain k0 to be equal to, well, either ek or minus ek. And, well, we're not interested in the negative energy solution. So we can get rid of one of those solutions by throwing in theta function, a Heaviside step function. And, well, this so this function doesn't look necessarily Lorentz invariant, but I'm going to argue that it is. So if we so this here just cares about the sign of the 0th component of a 4 vector. So if we do a boost, we're not going to change the sign. We'll change the magnitude of the energy, but we're not going to change the sign. So if we do a translation, likewise, we're not going to affect this sign. So the only part of the Lorentz group that could possibly change the sign would be if we change the direction of the arrow of time. That's not that's a discrete part of the Lorentz group. So if we just restrict ourselves to Lorentz transformations, that preserve the arrow of time, then this vector is invariant. So this is a Lorentz invariant way to write the measure. But you'll know from the front end, if we have a delta of a function, we get an extra factor if we want to write it as a delta so if we have a delta of f, we can write that as a sum over the roots of f of delta xi delta composed with f over f prime of xi. So we get this extra factor of 1 over the derivative evaluated at the roots of this equation. So this has roots at plus or minus ek. We're throwing away the minus ek because of this Heaviside function. So this, we do this integral, we get the measure we want with an extra factor of 2ek. And so this is our Lorentz invariant measure. And so it'll be convenient to rewrite this first line in terms of Lorentz invariant measure. And define some small a mode functions that are just related to the big A's from last time by factors of 2ek. A k is a of k over 2ek. So this form in the second line of the solution will be the one we'll use going forward. Any questions on that? Alicia?
Sure from there that since A and A star depend on just the three on momentum K, they are Lorentz invariant.
We're not sure. That's not something we know. We know that phi is Lorentz invariant. It's a scalar. So the integral of these A's has to be Lorentz invariant, but we don't know in general that they're. At least we can't directly see it from. In fact, these A's and A daggers are going to create momentum eigenstates, which will transform non-trivially to a Lorentz transformation. Okay, so on to quantization. So quantization is a four-step procedure, most of which we've already done. So our first step in constructing a quantum field theory using canonical quantization is to choose a Lagrangian. We did that last time. The Lagrangian we're going to study for now is the Klein-Gordon Lagrangian. Just has a kinetic term involving the derivatives and a mass term. And so here this Lagrangian is a classical Lagrangian. And if we want to end up with a Lorentz invariant quantum field theory, we also want to make sure we choose this to be Lorentz invariant. We choose the classical Lagrangian to be Lorentz invariant. That will guarantee that the quantum field theory is Lorentz invariant, which is one of the reasons we start with a Lagrangian instead of a Hamiltonian. The next step, which we've also done, is compute the conjugate momentum for each of the fields. Also, the Hamiltonian density will be a useful quantity. third step, which we'll do in a minute, to impose commutation relations. I've hinted at what those are, and you've seen those in your homework as well. We'll go through, I'll say a little bit more about that in a minute. And the fourth step, which may not be obvious yet why we have to do it, is to impose an ordering prescription. And I'll come back to this point. But if we don't do this, then the procedure is ambiguous. Okay, so just to recap, step one, we did this before. A Lagrangian is the Klein-Gordon Lagrangian. Done. So we'll consider more general Lagrangians later in the course. Step two, we also did last time, computed the conjugate momentum to the field. If we had multiple fields, we'd have to compute the conjugate momentum for each of them. And also, quantity that will be of interest is the Hamiltonian. We computed that last time as well. It's basically what you'd expect. We have here the kinetic energy term and radiant energy, and do this as potential energy. Okay, so that's those two steps we did last time. Step three. So this is where we'll impose commutation relations. So in quantum mechanics, what you would want to do is for each of your generalized coordinates and conjugate momenta to impose a commutation relation that's QA with PB. Suppose we've got many of them. Should be I delta AB. Remember, we're working in natural units where h bar is 1. And everything else commutes. So all of the generalized coordinates commute among themselves, as do the conjugate momenta. And what we're going to do now is just the generalization of this. So the only real difference now is that instead of a finite set of generalized coordinates, we can think about the field as being an infinite set, continuous set of generalized coordinates, one for each point in space. So the commutation relations we want to impose are that the field at each point in space obeys a commutation relation with the conjugate momentum. It's just I delta, a Dirac delta instead of Kronecker delta this time, delta x minus y. So this is a direct generalization of this equation here. Here A is the label labeling which one of the finite set of generalized coordinates we're talking about. Here x is a label that's talking about which point in space-time we're referring to, but we basically just have one generalized coordinate at each point in space-time or space.
And why do we put the commutation relations in tree space, in just space and not in space time?
For now, we're working in the Schrodinger picture. So I should have emphasized that again. So here, this is the Schrodinger picture. So our operators are time independent. We will come back to the Heisenberg picture where we'll impose a version like this that will have time dependence at the end of lecture, time permitting, or maybe the beginning of next lecture. Okay, and similarly, the fields and momenta all commute among themselves. And okay, so these are the commutation relations we want to impose. In your homework, you showed that these equations imply commutation relations for the ladder operators, which are the quantized versions of these mode functions from last time. So if we make this an operator, then over on the right-hand side, these have to become operators. And if we want to connect these Schrodinger picture field operators to what we did before, so we know that there's always some time in which the Heisenberg and Schrodinger pictures agree. I've made the choice that the time in which the Heisenberg and Schrodinger pictures agree are as at t equals 0. So if we want to get basically what we're quantizing here is the t equals 0 version of this equation. So in this equation, we're setting t equals 0 to get a Schrodinger picture operator. And so over here, the 0th component will just disappear, and we'll flip the sign, which is the version of the mode expansion you saw in your homework. So we set t equal to 0. The Schrodinger picture operator is related to the ladder operators just by setting t equal to 0. And so then we flip the signs because we only have the spatial components left. And so this is the operator, Schrodinger picture operator version of this equation you saw in your homework. And so you also saw in your homework that implies this commutation relation among the ladder operators. And the other quantity of interest is the Hamiltonian. Computed the classical Hamiltonian. It's here. So we can just directly use this expression to write the Hamiltonian operator in terms of the field and momentum operators. But it will also be useful to write the Hamiltonian operator in terms of the ladder operators. It involves some algebra, which you'll do in tutorial tomorrow, but I'll just quote the result. So the Hamiltonian operator is the integral d3k over 2 pi cubed 2ek. It's our Lorentz invariant measure that's going to show up again and again. Times half ek, ak dagger, ak plus ak, ak dagger. So this result, again, I'll show in tutorial later, suggests, well, if we look at this form of the Hamiltonian, it looks like we've got just a bunch of decoupled harmonic oscillators. So the integrand looks very much like the Hamiltonian you're used to for a harmonic oscillator. We've just got a lot of them, infinitely many. So that's useful to keep in mind. The free, you can think of the free quantum field as just infinitely many harmonic oscillators. Okay, so that's 3 out of 4 steps. So what's left to do? So step 4 says impose an ordering prescription. So why would we need to do that? Well, here's an example. So let's suppose instead of starting with the Klein-Gordon-Lagrangian in the form I've written it up there, we want to look at some different Lagrangian, which I'll call L prime, which is the Klein-Gordon-Lagrangian. But let's add phi dot minus phi dot phi. Okay, so classically, this is just 0. Everything commutes. This is 0 classically. So this is the same classical theory, so we might expect that we would get the same quantum theory if we followed through the first 3 steps and imposed commutation relations. But well, once we promote these things to operators, they no longer commute, and so we're going to get an extra term if we follow through the same procedure. And so there's an ambiguity in going from the classical theory to the quantum theory. We could add terms like this, which are 0. So we're in the same classical theory, but we'll end up with a different quantum theory depending on what kind of terms like this we add. And so we need an ordering prescription. So terms like this will only change the quantum theory up to commutator terms. So if we have an ordering prescription for the quantum theory, we prescribe some order in which the operators should appear, then we can remove this ambiguity and get a well-defined quantum theory. And I'll defer the question of what's a good ordering prescription for a few more minutes. We'll discuss the states first, and we'll see that there is a after we discuss the ground state of this theory, we'll see that there is a nice ordering prescription that we can impose and to get a well-defined quantum theory. Okay. Okay, so next part of lecture, discuss the states in Klein-Gordon theory, starting with the simplest state, the vacuum state. Which I'll denote as 0. But before I continue, are there any questions on the procedure itself? Yes.
I'm having trouble understanding what ordering prescription really means.
Okay, so if we follow through the procedure in the first 3 steps, we'll get an expression for the Hamiltonian, for instance. It involves these operators in this particular order. We are going to, if we added this term, we get something like this plus a commutator. Or in other words, we would be switching the order of some of these terms. And so what the ordering prescription is going to be is it's going to be a rule for how what order these ladder operators should appear in all of our expressions. So what the result is we're going to, after we apply our ordering prescription, we're going to, by hand, change the order of some of these operators. That's what we're going to do. Or in other words, we're going to add a particular, the commutator with a particular coefficient to this expression. Okay, so vacuum state, I'll denote by 0. So what do I mean by vacuum state? So the vacuum state satisfies AK acting on 0 is 0 for NEK. And we'll assume it's unit normalized. So in the quantum theory, the interpretation of these AKs and AK daggers there'll be operators that add or remove a particle with momentum, free momentum k from the state we apply them to. So for instance, if we apply, I'll say more about this in a minute, but if we applied AK dagger to our vacuum state, that would be a 1 particle state with momentum k. So this is saying we basically can't remove a particle from the vacuum. The vacuum is the state with no particles. If we apply these lowering operators that annihilate particles, we get nothing. Okay, so that's what the vacuum is. Let's try to determine some of its properties. One of the simplest things we could ask about the vacuum state is what is its energy. So let's apply the Hamiltonian to the vacuum state. And it's going to be, we'll get the ground state energy. It's going to turn out to be an energy eigenstate. So our Hamiltonian found is a Lorentz invariant measure, half over here, half EK. And then we have two terms, AK dagger, AK. We act with this term on the vacuum, we get 0, because AK annihilates the vacuum. So the only term that survives is the other term. And, well, the only thing we can do at this point is use our commutation relations, ones you derived in the homework. And what you get is we get a factor of 2 pi cubed 2ek, which cancels off with the denominator. We get a half ek, and then we get a delta of k minus k. So in our very first calculation in quantum field theory, we encounter a problem. We got infinity as our answer. Will be a common theme when we don't think very carefully about what we're doing. So what we did here is we just applied a Hamiltonian to the vacuum, and we get a delta of 0, which diverges and is problematic. We also have an integral over the energy. The energy grows with the magnitude of k, and we're integrating up to arbitrarily large k. So this is basically horribly divergent. So as we just start with that Hamiltonian, we haven't ordered in any way, we get infinity for the ground state energy. Now let's try to understand where this infinity comes from. This is really, let me go over here. This is really two infinities. An IR, or infrared, or low energy, and a UV, ultraviolet, or high energy, divergences. So one of the divergences is related to the delta of 0. And so, well, if we just think about a minute about what we're computing the energy that a field has in all of space. So if the energy density is, well, there's two possible reasons that could diverge. One is that if the energy density is finite, we're still dealing with an infinite volume of Minkowski space. So if the energy density is finite, we'd expect this to diverge because space is infinite. So that's one reason we might expect a divergence. And in fact, we can understand the delta of 0 as coming from the infinite volume of space-time. And to see that, we can imagine putting space in a box. So if we have a box with periodic boundary conditions, we can write 2 pi cubed delta of 0 as the limit L goes to infinity of this integral. So you all know that the delta, you can get the delta if we're doing an integral of an exponential. And, well, we're valuing that delta at 0, so p should be 0 in this formula. And here, when p equals 0, this is basically just the volume of space. So this delta, up to some factors of 2 pi, just delta of 0, one of the divergences just comes from the fact that space is infinite. This is an IR divergence, a long wavelength or low energy. And so maybe a better question to ask is, what's the energy density of the vacuum? The energy density should be the energy over the volume. Using our earlier expression, it's just E3k over 2 pi cubed and half EK. But this is still infinite. This grows like norm of k squared for k large. So this blows up like k to the 4th. Go to spherical coordinates, we've got a k squared. Okay, so this here is the IR divergence, and this here is UV. So how serious of a problem is this? Well, in non-gravitational physics, usually only energy differences are observable. So it's not a serious problem. Nevertheless, we know, based on the argument about the ambiguity, that we have to impose a ordering prescription in order to get a well-defined quantum field theory. So we might as well, even though this is not a serious problem because we can't directly observe it, we might as well impose an ordering prescription that gets rid of this issue and sets the vacuum energy to 0. So our ordering prescription is going to be called the normal ordering. And we'll denote the normal ordering procedure by putting dots on either side of the operator. And the normal ordered Hamiltonian will just be our original Hamiltonian, but by hand, we'll move all of the creation operators to the left and the annihilation operators to the right. So normal ordering two equivalent definitions. One, you can think of it as just if you have some string of operators. You just by hand move all of the creation operators to the left and annihilation operators to the right without using the commutator. Another way to think about it is you can think about a normal ordered version of an operator as an operator minus its vacuum expectation value, its expectation value in the vacuum state. And so step 4 of our quantization procedure is going to be to normal order all of our classical operators. And so most of the time I'll be writing these normal ordering symbols, but later on in the course, when it's clear from context that that's what we're doing, I may omit them. Yeah, so for other classical operators, it can be more of a problem that the vacuum expectation value doesn't vanish like the chart. So that's another reason why we do this. Okay, so this is a natural. Well, first, are there any questions about? Okay.
Lorentz invariant?
The vacuum state is Lorentz invariant.
How we can see this? Is it uniquely defined by?
That's we're making that assumption. Any other questions? All right.
So it's like
Okay, so the vacuum energy, the value of the vacuum energy is not something we can directly observe. But in a sense, there is a way we can measure the effects of the vacuum energy. And that's through something called the Casimir effect. So to illustrate what the Casimir effect is, let's work in 1 plus 1D for simplicity, the one space and one time dimension. And let's imagine that we've got two plates separated by a distance a. And let's suppose that these plates constrain the value of our field to vanish. Or these then these plates will constrain the allowed modes. And so if we computed the ground state energy in this case, we wouldn't have an integral because not all wavelengths would be allowed due to the presence of the plates. So we'd have a sum over the allowed modes. And so we could imagine that if we moved these plates, the vacuum energy would change, and that change in the energy would cause a force. And that effect is what's known as the Casimir effect. And it's been experimentally measured. So there were a number of experiments that were compatible with it or had weak detections, but it was first conclusively detected in '97, I believe, at the 5 or 10% level. So let's try to understand where that force comes from. Okay, so if we just are working in 1 plus 1D, and that one dimension is one spatial dimension is infinite, we'll expect an IR divergence just like we found before. So in order to simplify our lives, let's imagine that we put, we're working in 1 plus 1D in periodic space with period L. That's, say, much bigger than A. So picture over here, distance L. This is plate 1, plate 2. This is plate 1 again. So as we move one of these plates, the allowed modes will change, and so the vacuum energy will change, and we expect that to give us a force. Let's compute that force. So we have a box size of R, and the allowed frequencies are omega n are n pi over R. And ground state energy in this setup is going to come from 2 parts. There'll be some contribution to the vacuum energy from the fields in between plate 1 and plate 2 on this side. And there'll also be some contribution from the fields in between plate 1 and plate 2 on this side. So let's call those 2 contributions E of A and E of L minus A. Now, E of R should just be the sum of the energy of each of the modes, or the allowed modes. Which is this, which clearly diverges because the sum of the positive integers diverges. So that's not terribly surprising based on our previous experience. We got rid of the IR divergence by putting our theory in periodic space, but there's still a UV divergence. Arbitrarily, high energy modes are still allowed, and including all those arbitrarily high energy modes causes the energy to diverge. But as argued before, we can't directly measure the energy. What we care about is the force. And so the force is minus change in the energy as we change A. But if we compute that, so E of A, we'll get a term 1 over A squared. And the other one will get a minus 1 over L minus A squared times pi over 2 sum, again, of the positive integers. So it doesn't help. This is a force. So this, unlike having a infinite but unobservable vacuum energy, is a real problem. A force is something we'd expect to be able to measure. We can go out in a laboratory, and people have done this, and put 2 parallel plates next to each other. Do they attract, repel, or is there no force between them? That's a physical experiment we can do, and it's completely unreasonable to get infinity as a theoretical prediction for something that we can go out and measure in the lab. So we've clearly done something wrong here. And what we've done wrong is, well, we haven't made a very realistic model. So for any real plate, it's not going to be able to affect arbitrarily high energy modes or arbitrarily high frequency modes. So if we have a extremely high frequency mode, it's just going to pass right through the plate and will be completely unaffected. So we shouldn't, those arbitrarily high energy modes shouldn't contribute to the force because they don't interact with the plates. Okay, so we need some way to get rid of the arbitrarily high frequency modes. And a simple way to do that is just say that there's a maximum frequency, lambda, and only modes with omega less than pi lambda contribute. Okay, so if that's the case, then this sum shouldn't be from 1 to infinity. Instead, it should be up to lambda r, but n should be an integer, so it should be the floor function here. So this is the greatest integer less than. And in that case, E of r becomes pi over 2r, sum from n equals 1 and max of n. And max taking this value. And so this is a finite sum, which we can evaluate. Pi over 2r n max plus 1 over 2.
Sorry.
Yes?
Were you just on that? Is there reasoning for why high energy modes don't contribute?
Because they won't interact with the plate. So we can imagine we got a plate that's made of atoms. So if we have a mode that has a wavelength that's much smaller than the atoms, basically it will just go right through it, so it won't interact. But the thicker you made the plate, the higher you can push the cutoff, but there's always going to be some frequency that won't interact appreciably with. Okay. So this is the energy in between two plates separated by r. E naught, we need to add together E of A with E of L minus A. Skipping some algebra, the result is there's half a board of algebra that I'm not going to do in this equation. It's in this equal sign. The result is this, where x is the fractional part of lambda A. 5 or 10 minutes to do that algebra. I'm not gonna do it. There's nothing tricky there. Okay, so what does this look like? Plot E naught of A. So there's some, so x here is varying between, as we change A, is varying between 0 and 1, it's a fractional part. So there's a maximum value for E naught of A. That's just this other term. And this is oscillating. But as A gets bigger, the amplitude of the oscillations gets smaller. And the reason for this oscillation is as we change A, the energy of each of the modes changing, but at certain values of A, an extra mode will enter or leave our sum. That's why we get these jumps in the derivative. And so what we're going to want to compute is the force, which is the derivative here. We take lambda to be large. These oscillations are going to be very, very rapid. And so what we should be able to measure is the sort of the average. We change A, and L is lambda is very large. Then we're based on our experimental resolution. We're going to be changing it over many oscillations. What we can probably detect is the average over the oscillations. It just comes from integral x 1 minus x dx 6. And our force is in this case, even though if we take lambda to infinity, the energy will be infinite. The force is finite. We take the derivative. This constant term goes away. Just get the derivative of this term. And we get here the Casimir force, which, restoring units, is purely quantum mechanical force. Predicted in 1948 by Casimir, observed just 20 years ago by Lamoureux, inclusively. Okay, so this is kind of surprising. We got a finite answer, and it turned out to be the right one. Well, we've simplified things here by working with a scalar field and in 1 + 1 dimensions, but it works pretty similarly in more dimensions or with an electromagnetic field. Kitty.
Is it ever within the realm of experimental ability to measure those oscillations?
Okay. So right here in this derivation, I made a very crude approximation, right? I just said only certain modes contribute. Real materials probably don't work like that. Probably some modes that contribute more or less, depending on the frequency. It's probably a gradual thing. So one objection that you can and probably should make to this derivation is that this seems very ad hoc. We made some assumption about what's going on in the UV, which we don't know, didn't measure, don't have a good reason for that model. Got to find a prediction. The surprising thing that you'll explore a little bit more in tutorial is it really doesn't matter what model we put in for how the UV modes decouple. So in tutorial this afternoon, we'll explore another couple ways in which we can basically go through this argument, but making very different assumptions about what's going on in the UV. And the reason, if this was the only calculation Casimir did, it wouldn't be terribly convincing. The reason we believe his derivation and most of the calculations in QFT is that our calculations are independent of the regulator. So most of the time, this is very typical for how a calculation in QFT will work. If we do it naively, we'll get infinity. Usually, there'll be some UV divergence. So the problem here was that the arbitrarily high energy physics was spoiling our ability to make low energy predictions. And what typically occurs, the typical way you do a QFT calculation is we need to impose the UV regulator. Then we do the calculation. And if we've done everything correctly, the result should be independent of the regulator. So in our force, our regulator, lambda, dropped out. And we can remove it just by taking it to infinity. It doesn't show up in our final calculations, final answer, so it doesn't affect anything. So this is a procedure we'll do again and again. And the reason, one of the reasons we trust our calculations is that even though we don't always have physical arguments for why this particular regulator, or at least strong ones for why this particular regulator is a good one, once we do our calculation, our result will usually turn out to be independent of the regulator if we've done everything correctly. That's a procedure we'll be doing again and again. Yes.
The regulator is not Lorentz invariant, right? Like you are saying there is a maximum frequency?
That's right.
But with respect to which frame? Always go to
yes.
the frame where its frequency is very low.
Exactly. So that's another objection we could make. So I was implicitly working in the rest frame of the plates. But yes, many regulators introduce one problem or another. So sometimes one is technically easier, and that's usually the way we choose a regulator, but it's often not based on detailed physical reasoning about what the proper regulator should be. And so if you don't believe this yet, wait till tutorial. You'll see it doesn't matter what we do. We'll do it several other ways. Okay. So we spent most of class discussing the vacuum state. So now we can move on to the other states. As I alluded to before, the one particle states are the states that we get by acting with the creation operator on the vacuum state. And these are states of definite momentum and energy. I'm just labeling them by the free momentum that uniquely determines the form momentum, because these are physical states that we can measure that satisfy E squared equals K squared plus M squared. Okay, and so the other notable fact about one particle states is that, well, they're not unit normalized, and we can see that by just writing out the expansion. And as you showed in your homework, this commutator just gives us 2 pi cubed delta P minus K. So they're not unit normalized. The reason we chose the Lorentz invariant normalization of our measure when we solved the Klein-Gordon equation is so that these states are Lorentz covariant. So not unit normalized. These states are Lorentz covariant. So not every text chooses the same normalization that we're going to use. One of the main reasons for our choice of normalization is this fact that the states are Lorentz covariant. So the measure doesn't look as nice as some other choices of normalization, but there's nothing else to remember. Everything else behaves nicely under Lorentz transformations. Okay, so that's what the one particle momentum eigenstates look like. We don't have a position operator, as I emphasized in the last lecture, but there is a sense in which this state, where we act with the field operator on the vacuum, is a so this is a one particle state. We can show that. You can see that, erase the mode expansion, but this is linear in the creation operators. So it will create a superposition of momentum eigenstates, but it's linear in the creation operators, so that means it's a one particle state. And in a sense, it's localized at x. We don't have a position operator. So let me say what I mean by this statement that it's localized at x. If we compute the overlap of phi of this 5x and 0 with k, we get e to the minus I k dot x, which is the same as you would get if you took the overlap of a momentum eigenstate and a position eigenstate in quantum mechanics. So in that sense, it's like a Fourier transform of it has the same overlap with the momentum eigenstates as position eigenstate would in non-relativistic quantum mechanics. So in that sense, you can sort of think about it as it is a single particle, but you can think about it localized at x, and that'll be a useful interpretation, even though this it's not so straightforward to make this precise. It's not localized at x in the same sense that a position eigenstate is localized at x in non-relativistic quantum mechanics.
Now the uncertainty relationships are between the field and its momentum, its conjugate momentum.
Can you repeat the first part of that?
The uncertainty relationship.
Yes.
It's between phi and pi, and not between the.
That's right. Okay. And we can get multi-particle states. Just by acting repeatedly with our creation operators. So the state with n particles with momenta k1 through kn, then that's just a state where we apply the creation operators k1 up through akn on the vacuum. And well, we immediately see that because the AAK daggers all commute among themselves, these particles are bosons. So if we exchange two particles, we don't get any sign. And mute. Okay. And those are our multi-particle states. In the last few minutes, I just want to say a few words about the Heisenberg picture. So everything I've said so far has been in the Schrodinger picture. Heisenberg picture will be convenient for many of the calculations we'll do when we're setting up perturbation theory. We're dealing with interacting fields. And so you'll know the way to go from the relate operators in the Heisenberg picture to operators in the Schrodinger picture. In the Schrodinger picture, operators are time independent. In the Heisenberg picture, they depend on time. And the relation between the two is just the usual relation. Continues to hold in quantum field theory. And so we can show that the ladder operators, we write them in the Heisenberg picture, just e to the IHT times the annihilation operator, e to the minus IHT. And well, we can expand that out. That's AP plus So using e to the a, b, e to the minus a is b plus ab, so half a, b, etc. The BCH formula. We get this is h AP plus, and this is equal to minus, there's an I here, EAP. So AP T is equal to e to the minus I EPT AP. So the annihilation operator in the Heisenberg picture just evolves with the phase compared to the annihilation operator in the Schrodinger picture. And so that, using this and the analogous equation for the creation operator, it means we can write the Heisenberg picture field operator as AK e to the minus ik dot x plus a dagger e to the I k dot x. So exactly what you would guess based on our original solution, classical solution to the Klein-Gordon equation. We just replaced the mode functions. We had exactly the same expression here, except this was a k, this a star k. So this time evolution, it just gives us the missing phase that we set to 0 when we went to the Schrodinger picture and set t equals to 0. And so this is the Heisenberg picture field operator that depends on time. These are the same time-independent ladder operators that we had before. The phase, we just absorb the exponentials. Okay, so that's for a free field. For an interacting field, it's going to work the same way. The only difference for an interacting field, just to give you a preview of what we're going to do later, is that the ladder operators are going to have some additional time dependence. So for an interacting field, right, same mode expansion. And the only difference is that these mode functions are, or ladder operators in the quantum theory will have some additional time dependence, unlike the free case, where all of the time dependence in going from the Schrodinger to the Heisenberg picture is just this phase can absorb into the Katie?
So for the interactive field, if we go back to the Schrodinger picture, are those ladder operators still the same? And then we just change the exponential.
So at any one fixed time, with the Schrodinger picture and Heisenberg picture agree. We'll see this later. We can also make those agree with the free theory at any one fixed time. So in a sense, the answer is yes. We'll come back to that when we discuss this in more detail. Another way to argue that you can make this, so in an interacting theory, there should be some operators that create or annihilate particles. And what those operators are might change with time, but at any fixed time, there should be some operator like that. And so we should be able to write a mode expansion like this. The tricky part about dealing with an interacting field is figuring out what these time dependence is. And usually we won't be able to do that exactly. And so over the next few lectures, we'll develop techniques for dealing with interacting field theories, even if we can't find explicit expressions for these operators. Any other questions?
So are we gonna keep the same commutators now that we have the time that we are in the Heisenberg picture?
So those, for the ladder operators, they'll be the same. For the field operators, we'll have different expressions. So the time dependence will make for unequal times, the commutator will not be just I delta, a more involved expression. We'll get into that later. Any other questions? So starting tomorrow, we'll be going to the interacting case with cross sections and decay rates, trying to relate observables to things we can calculate in quantum field theory. So we'll do tomorrow, and I'll see you this afternoon.